Welcome back to this next video in our series. Today we'll have a look at a couple of examples for Gaussian elimination. We'll start with an example that you might already know if you've watched all the previous videos. Recall that we did an application at the very beginning of this section on Gaussian elimination, and that yielded an equation system. The idea was to emulate a target portfolio. We don't need to recap the details here. At this point, we just are interested in solving the resulting equation system. So recall the application basically emulating a target portfolio. That resulted in the following system of linear equations. And I'll give you the system in tableau form right away. So that was, the first row was 1, 3, 4, and the right hand side was 140. The second row was 2, 7, 10, with a right hand side of 320, and the third row was 1, 4, 9, and the right hand side was 225. So given this system of linear equations, we want to solve that system and of course determine if there actually is a solution. We start by selecting one of the leftmost elements that are not zero as pivot element. First step here is to choose one of the leftmost non-zero elements as the pivot element. For example, in this case here, we could choose pretty much any element in the first column. Here's that tableau once again. To make things a little easier, we'll just choose the element here in the first row. That has two advantages. First is we don't have to exchange rows because that row is already in the first row. Otherwise, we'd have to do some row exchanges now. Second is that pivot element is 1. And this will make the following computations a little easier, as you will see. So just have note of that. So this is already in row 1. That means no row exchanges are necessary. Nice. So the next step will be to turn the entries below that pivot to 0. So let's again copy the current status here. This is our current tableau. And what we want to do next is we want to turn the entries below that pivot here, these entries, we want to turn those to 0. Of course, that one as well. And we do that by adding suitable multiples of row 1 to the other 2 rows. So if we want to turn this entry here into 0, adding some multiple of that first row here. Well, what do we have to do? Here's a +1, here's a +2. So we need to multiply that first row by -2 and then add it to the second row. And that will give us -2 times 1 plus 2, that will be 0. So the idea here is to add -2 times the first row. And I'll usually denote rows by Roman numerals here so that you know what I'm doing in that step. Okay, let's complete that step first. What do we get? The first row is not changed. That will remain unchanged from this point on. So once we've selected that pivot and moved it to the correct position, that first row will never change anymore. Then we do this row operation. And that means we multiply that first row by -2 and then add the result to the second row. So -2 times 1 plus 2 is 0. Maybe write down that multiple here first. So we have -2 times 1, that's a -2. -2 times 3, that's a -6. And -2 times 4, that's -8. And of course, don't forget the right-hand side. -2 times 140 is -280. So that's that first row multiplied by 2. And adding that to the second row then yield following result. We get, well, 2 minus 2, 0. 7 minus 6, 1. And 10 minus 8 is 2. And for the right-hand side, 320 minus 280 is 40. Okay, so that's how we change the second row. Copy the third row for now, and we'll do that in the next step. Okay, so as you can see, we have our pivot here, and we have already gotten that first 0, and now we care about the second 0. Now what we need to do here is, well, here's a 1 in that position. So here we need to just subtract row number 1, or in other words, add -1 times row number 1. Okay, so let's do that as well. We don't change row number 1. Copy that. Also, we don't change row number 2 anymore, so let's copy that as well. For the third row, we add -1 times the first row, so let's compute that. -1 times the first row, that is -1, -3, -4, and -40. And adding that to the third row yields, well, 1 minus 1 is 0. That was the intention of that step. 4 minus 3 is 1. And 9 minus 4 is 5. And finally, for the right-hand side, we get 225 minus 140. that is 85. So that is our new tableau after that manipulation. Again, this was our pivot element. This here is the first staircase that we obtained. Right, so that was the first step. And now we repeat that procedure for the remaining part. So we'll select again a leftmost pivot element. We won't touch the first row anymore, so there's no pivot left in the first column because we turn that to zeros. So the leftmost is now the second column, or anything right to that second column if the second column would be an all zero column. So repeat that. Repeat the procedure for rows 2 to 3. Select a leftmost would that mean now is columns 2 to 3. Don't select the pivot from column 1 anymore. Non-zero element as pivot. So let's write down our current tableau first. We have 1, 3, 4, 0, 1, 2, 0, 1, 5. And the right hand side is 140, 40, and 85. And we can select any two of these entries. And remember, we don't touch the first row, so the pivot cannot come from the first row, but it can come from any of the other remaining rows. And here we have two non-zero elements, 1 and 1. Both are suitable as a pivot element. We just choose the first one here, but we don't have to do row exchange. The second one would work as well. Okay, so this is our pivot. And using that pivot, we are now going to do row operations to produce zeros below that pivot element. So we want zeros here. Okay, so next step is again perform row operations on rows 2 to 3. Return the column below pivot into 0 entries. And that's just one row operation that we have to perform here. So do that again. So in this case, there's this row left with a 1 entry, and here's a 1 entry as well. So we just need to subtract that second row, or add a multiple of -1 times the second row. Okay, I'll make this a little quicker now. Again, we just copy rows 1 and 2. Row 2 will never be touched from this point on as well. And then we do the computations with all the rows below. One row for this example here. So we have here is, well, obviously nothing changes in that first column. Yeah, 0 plus 0 times whatever you want is still 0. So we can simply copy that 0. And then start here. What we get is, well, 1 minus 1 is 0. That is what we wanted, so that's nice. And here we have 5 minus 2, that's 3. And for the right-hand side, we get 85 minus 40, that is 45. And now we're at the point where we have echelon form, like this. Here's our two selected pivots. And the third round, you have to consider, sorry, that's the third column. You have to consider that one as well. The third column also contains a pivot because this element here is non-zero. Okay, so those are the pivots. You have 3 pivots in echelon form. We have 3 variables, so that means we don't have any free parameters in that system. 3 pivots, 3 variables. That means no free variables. So if there is a solution, then we'll only get one single unique solution here. Now, let's try to solve that system right away. So next step we do is solution through backward substitution. Copy that tableau here. What we want to do is we want to start at the last pivot, so the last column that has a pivot, that is this column here. And that corresponds to the variable x3. So first thing we get is 3x3 equals 45. And it's easy to solve this for x3. By just dividing by 3, we get x3 must be 15. Second thing we can do is look at this pivot element here corresponds to x2. And take the x2 row here. That yields x2 times 1 plus 2x3 equals 40. And obviously that means x2 is 40 minus 2x3. We know x3 already, so that's 40 minus 30, that is 10. Right, so here used that x3 is 15, so 2 times x3 is 30, and that yields a value of 10 for our x2. And finally, here's our x1 column. Also has a pivot, so we can solve for that x1. And the first row corresponds to the equation x1 plus 3x2 plus 4x3 equals 140. So that is equal to x1 equals 140 minus 3x2 minus 4x3. And again, let's substitute the values that we know already. So we know that x3 equals 15, and we know that x2 equals 10. So we get 140 minus 3 times 10, that's 30, minus 4 times 15, that's 60. So we have 140 minus 30 minus 60. That yields 50. So our solution is x1 equals 50, x2 equals 10, x3 equals 15. Or, in other words, the solution set or solution space is S. And that we usually just write those numbers in the correct order, starting with x1, 2, then x3. So x1 is 50, x2 is 10, x3 is 15, and we write them as a 3-tuple in this way. Okay, the reason for that will become more obvious in later sections when we talk about vectors and vector spaces. But for now, just remember that's the way to write a solution. Okay, so this is a single unique solution in this case. Now, let's have a look at one other example. In this case, I'll start with the system of linear equations right away. So that system is x1 plus 4x2, 2x3 equals 5, x1 plus 6x2 plus 3x3 equals 6, and x1 plus 8x2 plus 4x3 equals 7. We'll translate that into tableau form first. And the tableau form for that is, well, the first row is 1, 4, 2, and the right-hand side of 5. Then we have 1, 6, 3, and the right-hand side of 6, and 1, 8, 4, and the right-hand side of 7. Let's select the pivot element. Again, in the first column, we have 3 non-zero entries. Any one of those would do. So we just choose the easiest one, and that's this entry here. They are all ones, so that doesn't matter. We just choose the one in the first row, though we don't have to move rows. Next, we'll use that entry to produce zeros down here. And of course, that can be done by just subtracting the first row from the second and by subtracting the first row from the third. I'll do both of these in one step now, and I'll also just write minus row 1 as an abbreviation of plus minus 1 times row 1. Okay? So what we get doing this step, the first row is not touched anymore, so we just copy that. 1, 4, 2, 5. For the second row, we get 1 minus 1, that's 0. 6 minus 4 is 2. 3 minus 2 is 1. And 6 minus 5 is also 1. And for the third row, we get 1 minus 1 is 0. 8 minus 4 is 4. 4 minus 2 is 2. And 7 minus 5 is 2. So we have obtained the first zero column here. And now we're going on with the next step. So the next pivot from row 2 and 3. The leftmost entry, we could choose either this 2 here or this 4. Any of those would do. And to make things a little easier, we just choose the 2. Now we want to produce zeros below that 2. So in this third row here. Now to do that, we have to subtract the second row from the third with a factor of 2. So that's minus 2 times the second row. And that yields the following result. So we copy rows 1 and 2. Those will not be touched anymore. And the third row then becomes, well, there's a 0. Then we have 4 minus 2 times 2. So 4 minus 4, that is 0. And 2 minus 2 times 1. 2 minus 2, that's also 0. And for the right-hand side, 2 minus 2 times 1, that's again 0. So as you can see here, I have now obtained echelon form with a pivot here and a pivot here. However, there is no pivot in column 3, row 3. Remember, we can only choose pivots below the rows that already have pivots, right? So for the pivot in column 3, we are bound to row 3, and there is only 0 entries in there. So the leftmost is also a 0 entry. There's just no pivot. So in this case, we have no pivot in this column. And what does that mean? Well, that means the variable corresponding to that column, which is x3, is free variable. Corresponding variable 3 is free variable. So for the solution process, we'll again use back substitution. I will just make a quick note that x3 is free. So all the following results might depend on x3. For the second column, this one here, that's the x2 column. We can take the second row, that's the equation 2x2 plus x3 equals 1. So solving that for x2 yields x2 equals 1 over 2 minus 1 over 2 x3. Notice the result does depend on x3. Now that's fine. Every value of x3 has a corresponding value of x2 such that we get a solution. And finally, let's go for x1 as well. Now x1, do it for x1. So we need this first row here. The equation here is x1 plus 4x2 plus 2x3 equals 5. So we get x1 equals 5 minus 4x2 minus 2x3. And that is, well, 5. Then we can use x2. We know that already. So let's substitute that here. Minus 4, and x2 is 1 over 2 minus 1 over 2x3. And then we have minus 2x3. x3 is free, so we can't substitute anything for that. So what do we get? Well, that's 5 minus, let's see, 4 times 1 over 2 is 2. And then we have plus 2x3 minus 2x3. So effectively the x3 terms cancel out and we get 5 minus 2, and that's 3. So as you can see, x1 does not depend on x3. That can also happen. It does not have to depend on any of the free variables. It can depend on them. So what's our solution space? Yes. Let's see, x1 is 3. So that's easy. x2 is 1 over 2 minus 1 over 2 x3. And x3, the free variable, is just itself. So we just write x3 here and take n on any value. And taking on any value means we can select x3 in R. So this is the set of solutions here. We can write this a little differently to make the structure more clear by separating the constant terms and the terms corresponding to each of the free variables. And we usually do that. So the constant terms here are 3, 1 over 2, and 0. Then we have x3 times, here we have no x3 in the first coordinate, minus 1 over 2 in the second coordinate, and 1 in the third coordinate. And again, x3 is any real number. So what you can see here in this last representation is the geometry of this solution space. How does that look like? We have here is basically a set that lives in three-dimensional space. And what we do is we take this point here, and then we add some multiple of this vector here. So we have a point we start at, and we add some scaled version of a vector, so we can like go into this constant direction any distance we want. So what we get here is a line in 3D space. Goes through this first point and has this direction here. Okay, so that solution set S is a line in 3D space R3 through the point 3, 1 over 2, 0, and in direction 0, minus 1 over 2, 1. We'll discuss this structure of solution spaces in more detail in our later chapters. For now, the idea is to give you a procedure of how to solve arbitrary systems of linear equations. A word of warning at the end. Gaussian elimination is, of course, by no means the only method that you can use to solve systems of linear equations. We've seen other methods in our examples before, and from school you're basically used to other methods as well. However, Gaussian elimination is probably the most systematic approach that you can use. And that's why I recommend using it. It minimizes the probability of errors, in my opinion. So, especially for larger systems, it's probably a very good idea to just stick to Gaussian elimination, practice that, see to being good at Gaussian elimination, and then you don't need to take care of all these other methods that you may also know. Also, we will use this same procedure as in Gaussian elimination in other contexts as well. So you will need that anyway. And if you need that anyway and have to practice it anyway, why not use it everywhere? Probably easier, and again, it minimizes the risk of errors and failure. So, not much about examples about Gaussian elimination. You'll see more examples in the exercises, of course. And I'll see you in one of the upcoming videos.